Friends, I think I have delivered so far some 11 lectures, and in the last lecture I was winding up discussions on general principles of extraction and refining. After that, I have taken about a month's break, because I wanted to think, what was I doing? Was I doing things right? Could it have been done differently? Is there something I am missing out? Now, frankly, I mentioned that before, that the way I am lecturing now is very different from the way, say, I would lecture in a classroom, where I have more degrees of freedom. I can walk about, I can look at students who are actually present, I can interact with them, they ask questions. If I make a mistake, I can go to the board and wipe it and restart it. In fact, I can repeat a class, do it differently. But in this arrangement, the way I am lecturing now, there are more constraints. I am in one place, there are cameras on me, I have to finish certain things within a specific time slot. There is no room for mistakes. I cannot wipe the board, and therefore, I have to acquire a new experience, which I am acquiring. Hopefully, I will do better now. Now, the first question I asked during the break I took was, what was it that I was aiming at? So, obviously, my aim is to help you learn the subject of extraction of non-ferrous metals. Now, the emphasis is on learning, not on my teaching. I can assume that I am teaching a lot of things, but if you are not learning, then what is it I am teaching? So, let me tell you something about the learning process. In learning, there are several steps. The first comprise facts. You need to have facts about things, because you do not have facts, you do not know things. Facts, when they are organized properly, give you information, and information is distilled into knowledge. Now, my job as a teacher is to give you some facts, show you how information comes from those facts, and help you acquire knowledge from that information. Now, in this process, as a teacher, I have to strike balance between facts, information, and knowledge. I am suddenly reminded of a very beautiful statement of the famous English writer, poet T.S. Eliot. Eliot once said, rather lamented, where is the information lost in facts? Where is the knowledge lost in information? And where is the wisdom lost in knowledge? Actually, T.S. Eliot said the last two sentences. I have added the first one, because it is just as relevant. The meaning of this is that if you have far too many facts, then you miss out on information. The information you need is merged into a mass of things, facts, some of which may not be necessary. Again, if you have far too much information, it becomes difficult to acquire knowledge out of it. And you also know that there are many people who have a lot of knowledge, but they are not wise. Now, what is wisdom? Wisdom is application of knowledge. This is not what I am going to try to teach you, because wisdom has to come from within you. You have to learn how to apply the knowledge you acquire. So, as a teacher, and I am not a guru, guru gives you wisdom. As a teacher, I can give you facts. I can show you how facts go to information, then show you how information goes to knowledge, and I will stop there. So, if you acquire a bit of knowledge, I will be very happy. Now, let me give you some example about how, what is the distinction between facts, knowledge, and facts, information, and knowledge. Imagine that I want to study the kind of vehicles, two-wheelers and four-wheelers that are there in this campus and the role they play in the society. Now, you can always get some volunteers to acquire information about facts, not information, facts about two-wheelers and four-wheelers. They stand in street corners, they go from house to house, they go to the registration authority where vehicles are registered, and they get a total information on how many two-wheelers are there, how many four-wheelers are there, and so on. Now, they can also acquire a lot of unnecessary information, which perhaps are not required, like how old the vehicles are, what is the condition of the vehicle, what color they are, etc., etc. We do not want that. What I want, I will tell you later. Now, when you have a whole lot of data about the ownership of two-wheelers and four-wheelers, you cannot distill the information, distill these facts into in an organized manner to get some information. Like, you can find out about the ownership of these two-wheelers and four-wheelers. How many students own two-wheelers or four-wheelers? How does the ownership depend on age groups, income levels, spread across students, teachers, and supporting staff? How it depends on the number of people in the family who have regular income, etc., etc., etc. Now, when you get this sort of things, when you have organized the facts into a higher level, then you get information. Then we try to get a knowledge that, okay, let us analyze the disparity in ownership of vehicles amongst different income levels, different social strata, and the implications of these. There will be some disparity. Is it right? Is it wrong? Should we bring in public transport system? Should we bring in more rickshaws? Should we bring in buses? This will depend on practicality, on traditions, what is tolerated in the society. Then we are going towards knowledge as to how we best utilize the information we now have from facts to bring in more harmony, more justice, etc., etc., in the society. That will be knowledge. Now, in the industry also, there are a lot of facts. If you go to any industry, you will find there are recording instruments which are constantly measuring things. There are some people whose job is to collect facts and stop there. Then a higher level of personnel come who organize these facts into information that go to executives who from the information acquire knowledge. Now, in that process you will find one has to decide on how to handle contradictory requirements. In a society, in a family, in an industry, everywhere, there are contradictory requirements. Means if you want to do this, then something else suffer. Then you have to find out what is the compromise. Now, I think I am becoming a little more philosophical. So, I will bring it to similar questions in an industrial setup. And for that I thought I will take 2 more lectures as concluding remarks for the module 4, which I was discussing last time. So, let us look at the first slide, which is about concluding remarks for module 4. Now, so far we have discussed some general principles of extraction and refining of metals. These are to be suitably used to meet the needs of the industry, taking into account contradictory requirements, the actual situation prevailing, etc., etc., etc. Now, there are 3 very important requirements for any industry, and they are floor space, energy requirement and productivity. Now, not that these are the only requirements, there are other requirements, for example, of capital, labor, environmental problems, many other things. But let me restrict myself to 3 questions: that floor space to be kept low, energy requirement should be minimum, productivity should be high. Now, if you consider pyrometallurgical operations, it is quite obvious that they need less space and productivity can be high, because very often use reactors or furnaces which operate at high temperature, and at high temperature reaction rates are accelerated. But then when you are operating at high temperature, energy requirements can be high, because there may be heat losses. Of course, in many pyrometallurgical operations, heat is also recovered from the gases that are coming out as hot gases. This will minimize the heat requirement if you can recover the heat. Secondly, contrary to what we may think that all pyrometallurgical operations need a lot of heat, there are also many reactions which are exothermic. For example, we will consider when we go to copper metallurgy. When you roast copper, it requires high temperature, but roasting is exothermic. It almost proceeds by itself if you do not allow too much of heat losses. Smelting, next step, or after that we will come to blister copper formation. They are all exothermic. In theory, everything can be done without supply of external heat, but that is not possible, because in practice there will be heat losses. But anyway, in general you should think that in pyrometallurgy you are operating at high temperatures. So, obviously, one should think that energy requirements should be high, but then space will be limited, because in a small reactor simply by increasing the temperature you can produce a lot. Not that you can go on increasing the temperature, you cannot do that. There are many limiting things. For example, one limitation are the refractories. Refractories cannot take more than a certain temperature level. Secondly, you do not need all kinds of unwanted reactions. If you go to very high temperatures, things may happen which you do not want to happen. So, not that the upper temperature is unlimited, but we can go to high temperatures, accelerate reaction rates. Now, compare that to hydrometallurgical, electrometallurgical operations, which are consider first hydrometallurgy, which is always near below 100 degrees, because we are using hydromedium. Also in electrometallurgy you can have aqueous electrolysis, there also temperatures are low, but these cannot be done in very limited spaces, because when you are handling liquids you need pipelines, you need plumbing, you need floor space, and also because the temperatures are low, reaction rates cannot be high. So, the space requirement will not be low, space requirement should be high. Now, all this can be understood through common sets, but you can bring in some amount of quantification also, bring in a bit of theory. I will try to give you some examples of that, how you can be more rational when you make statements like this. We will also discuss some concrete examples of contradictions. Now, let us start with by considering an electrolytic cell. Now, in electrolytic cell you apply a voltage, you pass some current, voltage into current is the energy requirement, and you produce the metal. Now, the first question is, will you produce more metal by giving more energy through increase in voltage? You increase voltage. So, more energy, voltage into current, would you produce more metal? The clear answer to that is no, because there amount of metal you are going to deposit on the cathode has nothing to do with the voltage. It is, according to Faraday's laws, governed only by the current that is being passed, and Faraday gave two laws. One is amount is directly proportional to the current passed, and it is proportional to the equivalent weight of the metal. We need a voltage simply to make possible dissociation of the solute, and there the idea is to keep the voltage to the minimum. We need only the voltage that is required for dissociation of the solute. Unfortunately, we always need to have some excess voltage, because voltage is also required to overcome the resistance of the electrolyte, the electronic resistance in the circuit, and the electronic resistance in the electrodes themselves. Now, when the electrolysis takes place at a higher temperature, then the resistance of the bath is used to generate heat, because there will be a voltage loss. There is a resistance of the electrolyte, a current is going through, and there is an I square R amount of energy that is not lost really, but that is what keeps the melt hot. So, while you need a voltage for dissociation of the solute, you would also need for high temperature electrolysis certain amount of voltage to be lost for heating of the electrolyte. This you will not need for room temperature electrolysis. Now, all these can be analyzed very, very rationally using simple theory. I cannot go into all this, but I will discuss something which common sense tells us, but we can prove with little bit of mathematics. That is, suppose I have an electrode. Now, you know the electrode surface where the metal is deposited, that area is very important. The larger the area, the more metal can be deposited. So, there is a concept of limiting and the current density, current passed per unit area of the electrode. If the area is made very large, there can be more current. So, more metal can be deposited. Now, the electrode area can be increased in many ways. The electrode can be made very wide, or it can be made very deep. Now, if you make an electrode which is very wide, like the blackboard, say, in the horizontal blackboard, the area is very large. But if you do that, you are taking more floor area. So, suppose somebody says, why not put the blackboard the other way, so that it is a very deep, it goes below ground, you dig it below ground, or make the cell vertical, make a long high electrode. Can we do that? The answer is no. We can show why through very simple logic that if you make the electrode very tall, then you are going to increase its resistance far too much. And so, you will be losing voltage there, and that voltage does you nothing, it simply heats up the electrode. Necessarily the electrode has to be wide and not tall. How do we prove that? Let us consider, we will consider two electrodes sitting side by side, and the current is, these are the current feeders. Let us consider the anode. Current comes from the top and it flows towards the cathode. Now, let us call this distance x, the distance to which the current is travelling, and the elemental distance is dx. We call the width w, the total height, length, you can call it is L, and the thickness T A, thickness of anode. Now, let us analyze this situation simply to find out where resistance will be higher. Will it be higher if this dimension is very high, or if that dimension is very high? Now, electrode resistance I have written here depends on how good the connection is with the bus bar carrying current and its geometry. This we are going to ignore, means how it is connected here, this connection is also vital importance in the industry, because that will be part of electrode resistance. Let us ignore that. That is a technical problem, that we must find ways of connecting this electrode to the feeder in a way so that there is very little resistance in the connection. But once you have done it, the voltage drop between electrodes will be what? It will be I into d by L w. I is the total current, d is the distance between them, and L w gives you the total area of the electrode, and this we can write as I d, where I is the current density. Now, consider voltage drop across only this part of it, that as you come down, voltage of across an elemental dx, let us assume. Now, there we first make an assumption that the current density is independent of the height, means same amount of current is flowing per unit area. This is exactly not right, there is small error in that assumption. To this I will come to the later on. Now, the voltage drop across an elemental height dx is dV, elemental voltage drop, rho A, that is resistivity of the anode, Ix total current, and dx, total current is coming through this, divided by TAW, that is the total area. Okay. Now, what is Ix? Ix is nothing but current density into Na, means on how many sides it is active. Now, there are cells where only one side is active, there are reasons other side is active. This can be 1 or 2, Ta plus W, Ta plus W gives you this by this, the cross section through which the current is flowing, into x, it is the elemental height. Now, substitute for Ix from here, So, we will by combining these two equations get an equation which is elemental drop in voltage across the dx is current density into resistivity into number of size of the electrode in operation T A plus W, that is the cross section available, into x T x divided by T A W. Now, note here generally the thickness is very small compared to the width. So, we are going to ignore T A in comparison to W. Now, if we integrate from 0 to x, we get the total potential drop from the bottom of the anode to a height x, and that comes as delta V is equal to this. Now, maximum potential drop will occur at x equal to L, means at the terminal, and substituting and noting that W is greater than the thickness, we get finally an expression for the voltage drop maximum across the entire height of the electrode as this. I is the current density, N is the number of sites that are relevant, 1 or 2, this is resistivity, it should actually be a rho, L square is the length square divided by 2 T A, which is the thickness of the anode. Now, you see in this equation there is no width, means width does not play a role in increasing or decreasing the resistance of the electrode, which means you can make it as wide as you can, increase the area of the electrode that way, increase the width, it is not going to change the resistance. On the other hand, L square, this is a big culprit, L, the resistance increases in proportional to square of the height of the electrode. So, obviously, the equation shows that the resistance reduces for thicker electrodes, this we know, it is always there for thicker electrodes, and shorter electrodes, the width is immaterial. So, what does the industry do? The industry simply cannot have very deep electrolytic cells. It does not mean they will be minuscule, there are some practical things after all. You cannot take a electrode which is only this high and 10 meters wide, no. But by and large the height has to be limited, width can be broad, because width is not adding to the resistance, and the electrode should be thick and wide. Now, I had referred to this, that I means the current that is coming and flowing to the other electrode, that current per unit area actually changes as it goes down the electrode, and rigorous calculation shows that delta V will change by about 30%. It will change about, however, the basic observations about the width does not change. Delta V according to final calculation will change, but it is still immaterial, width is immaterial. So, the final conclusion will come to this is this, that all electrolytic cells will have to have thick electrodes, as thick as possible. They will have to be shallow as practicable, and they have to be wide in terms of the electrode width, as wide as practicable. Now, there are practical limitations everywhere, and that is the industry has to decide where is the optimum from the point of view of operational facilities, practicalities of production, etcetera, etcetera, etcetera. But some substances, that since you are going for width and not for depth, you are going to take more floor area. You cannot do the operations in a small floor area. So, these are the implications. We cannot use deep or tall cells, and therefore, wider electrodes will acquire greater floor space. Now, let us talk about productivity. Okay, we can increase the productivity by making the electrode wide. That is one way, because the wider the area, or rather bigger the area, more current can be used to deposit more metal on the electrode surface. But then there is a catch again. There is a maximum limit to which you can increase the current for a given area of the electrode. Just because you have an electrode area and the Faraday's law says more current means more metal production, you cannot go on increasing the current. Why you cannot do that? To understand that, we have to find out, we have to analyze and the mechanism of deposition. So, here is an electrode surface and current is bringing metallic ions to this cathode for deposition. It is a negative electrode, positive ions are coming to deposit. More current means greater flux of metal ions, that per unit time more number of ions are coming. So, increase the current means more and more ions are coming. Now, when the ions come, they have to get discharged at the surface. From metal ions, they have to become metal depositor. And so, the process of depositing metal on an electrode during electrolysis, it is two-step process. The first is diffusion of metal ions to the surface, then discharge of metal ions at the surface. These are two distinct steps. Metal ions come through the bulk of the electrolyte because the current is pushing it. It gets discharged by a reaction where metal ions take up electrons and get themselves deposited. So, we have a diffusion step and an ion exchange and electron exchange step. Now, it so happens that in most cases the second step is fast, means the moment metal ion comes to the surface, it gets discharged and metal deposits. So, in such this situation we call diffusion controlled reaction. So, the rate does not depend on the rate of transfer of charge at the surface, rate depends on the rate at which it is coming through the solution, through the electrolyte, and that is through diffusion. How does it happen? It happens because of this, that this is the surface of the electrode, this is the bulk, current is pushing the ions towards the surface, and as it gets discharged, its concentration at the surface drops. So, you have a concentration profile, and because of this concentration gradient, diffusion takes place. Now, when you want to increase the rate of diffusion, means rate of transfer of metal ions to the surface, what happens is this profile changes, means you have a greater gradient here, because unless you have a greater gradient, you cannot have a greater diffusion flux. But then as you increase the current, surface concentration drops to make the gradient steeper to allow greater diffusion rate, but there is a limit, because when you increase the current far too much and to sustain that, the surface concentration drops, at some stop it drops to 0. Means now you are passing so much of current, and to sustain that there is so much of gradient now, because unless there is a gradient there cannot be diffusion. Now, at this surface you have brought it down to 0. This is the limiting current, because when it falls to 0, you have a limiting gradient, and that limiting gradient defines how much current you can send. This becomes the limiting current, and limiting current divided by the area of the electrode becomes limiting density. So, in any cell, your first goal will be to increase the surface area. Having increased the surface area, your goal will be to increase the current, so that you can produce more metal. As you increase the current, how will the current be sustained? Because it is a diffusion controlled process, there will be more gradient. But beyond a certain level of current, the surface concentration of metal ions falls to 0. There is nothing left, and therefore, it cannot go down any further. That is the limiting current density. So, in any given cell, if it is a diffusion controlled process, which most metal deposition processes are, there is a limit. And this limiting current concept is of vital importance in electrometallurgical operations. So, I will quickly go through again this. Higher production, we need more current per unit area for more cathode area. Step 1 is cations diffused towards the cathode surface. Step 2 is cations are discharged to the deposit metal. With higher current, the concentration, this should be C, concentration profile is steeper to push more ions towards the electrode, and then finally, we end up with the limiting current. Now, suppose we have an electrode now, and there is a limiting current. What do you do? This question has been asked by many scientists in many ways. But before I go to that, whatever I have said, let me put it down mathematically, because these are all subject to mathematical analysis. We can say that we have limiting current density because we can pass more current if electrode area is increased, not otherwise. What are the equations? Basically, an oxidized species like say metal ion is at the surface acquiring electrons to produce a reduced species. The potential for that is given by the Nernst equation. Now, you can reverse that and put it this way also, where E is the single electrode potential, A is activity of oxidized or reduced species. With passage of current, E changes to E plus eta C. This eta C is what we call the cathode over potential, because the potential depends on metal in concentration with metal ion. Now, if the metal ion concentration is dropping at the surface because of the diffusion phenomenon, then the electrode potential will change, and the change is the cathode over potential, because the process being diffusion controlled. So, this we can calculate as R T by N f, this is N f ln activity of the species at the surface divided by activity of the oxidized species in the 0 or bulk activity at the surface. For dilute solutions as well as fused salts, this value we can calculate. How will you calculate? Because first of all, dilute solutions, let us replace activity by concentration. Now, the similar equation will be true for anode also. Now, molar flux per unit area is total flux divided by A, which is a constant, into C naught minus C s naught. C naught is the bulk concentration and C s is surface concentration, is the diffusion coefficient, and where K m is d by delta, d is the diffusion coefficient and delta is the boundary layer thickness. You are aware with the diffusion equations. According to Faraday, this equals total current divided by valence into Faraday constant F. Therefore, I that the current per unit area, we can get an expression. In a limiting case, where the surface concentration falls to 0, the limiting current density I d is given by this expression. valency, Faraday constant, and surface concentration in the bulk. Now, what is then the value of the overpotential? We can make substitution and get an expression that the cathode overpotential is given by an expression, which is a function of current density and limiting current density. Now, for aqueous solutions, diffusion coefficient generally has this value, delta, that is the boundary layer thickness, has about this value, and concentrations are generally 10 to the power 3 moles per metric cube. So, ID approximately comes to this, that in many processes the limiting current density is 10 to the power 5 amperes per meter square. Per meter square you cannot pass more than 10 to the power 5. Now, this is very important. There is another thing, we can calculate the overpotential, but this comes out to be only a few millivolts. This is true for few salts also. So, the phenomenon on overpotential does not change the voltage requirement much, which is a good thing. That because there is a overpotential, that does not mean that we need to apply lot more voltage now. That is not required, because the overpotential is only a few millivolts, whereas in most cases you will need some volts, several volts for electricity. But what is important is that there is a limiting current density, and in most operations you will not be able to pass more than 10 to the power 5 amperes per meter square. Now, what are the implications? Implications are that if metal deposition is diffusion controlled, which is the fact in most metal deposition processes, in that case we change the electrode potential at the surface, but change it very little, by a few millivolts. So, the voltage requirement does not change, but that phenomenon gives rise to a limiting current condition, and we can calculate the limiting current in most cases to be about 10 to the power 5 A per meter square. So, you see that a simple phenomenon of electrolysis, if we try to analyze it, think little deeply, we come out with this very interesting and vital findings, and we can do quantification also, as I have tried to do. So, let us summarize the implications now. Implications are that metal deposition on cathode is often diffusion controlled, and this sets a limit for the current density. Thus, metal deposition per unit cathode area has a maximum limit, and that will correspond to 10 to the 5 amperes per meter square. You can calculate how much of metal deposition according to Faraday's law, taking into account the equivalent weight. Now, to increase productivity in a cell, one needs more cathode area. Therefore, either you make the cell very wide or have more cells. You can have multiple cells, which means you will need a lot of floor area. But definitely you can have wider, but not deeper electrodes. So, generally we will have an array of electrolytic cells, which will occupy a lot of floor area. Thirdly, the concentration over potential does not change the decomposition voltage much, but the phenomena leads to a limiting current density, which is of paramount interest, which I have repeated many times. One can think of other ways of increasing cathode surface area. Can we change the cathode surface area in some other ways? To this I will come little later, but before that let us consider how we arrange multiple cells. See, we need more cathode area. Since we can have only a certain amount of production in one cell. So, we need multiple cells. To obtain more cathode area. Like say for example, we have one electrolytic cell, we have another, then each we have a cathode and anode and cathode and anode and cathode and anode. How do we arrange these cells? One will be to have them in series. If you have them in series, then the same current flows through all. One current flows from one into the other. So, current low in the sense as much as you need as per the limiting current density. But the voltages V 1, V 2, V 3, they will add up. From here to here, you need greater voltage, the voltage adds up. On the other hand, what one can do is, suppose you have these 3 cells, they can be in parallel. What will that mean? This will mean you are feeding current to each. So, you will need more current here, greater current. But voltage is common between this and this. Voltage is coming from the voltage remains the same. So, you have a choice between a series arrangement where we have lower current because the same current is flowing through, but higher voltage because voltages adds up, or you can have a parallel arrangement. Where we have higher current because the current will get split into different things, but you will have lower voltage because from 2 common grids all of them can be operated. Now, question is this better or is this better? Now, if you analyze, the power requirement would be the same because power is I into V. Here I is low, V gets multiplied by N into V, NIV. Here current is high, NI, voltage is V, NIV. The energy is the same. But then what will the industry do? There you have to take into account practicality and also little bit of common sense. Suppose you put everything in a series arrangement, means one after another these cells are in series. Now, in a series arrangement, the problem is if one cell goes out of order, you want to shut it down for repair, then the entire line is out of operation. Get that? It is like if you have a whole lot of clerks or working in an office, a file goes from one desk to another desk, from that desk to another desk, to that desk to another desk. Now, if one clerk takes leave, then the entire chain of operation stops. which industry cannot allow. There is the advantage that you are taking a lower amount of current which is going through and all, and maybe you can do with more voltage. On the other hand, in a parallel arrangement, if one goes out of order and you need some repair or you need something, then you remove it, does not matter, the others are operating. The current does not go through that, but the current goes through the other things. And that is what is done in many offices also, that we never put everybody in series. We always have a parallel arrangement also, a safety valve kind of thing, that okay, if this process is not working, the others are working. So, industry would not like to have put everything in series, never, but there are advantages. Now, if you put everybody in parallel, there is a disadvantage, apparent disadvantage. What is the disadvantage? That when they are in parallel, the current that is coming is getting split into different streams. So, you need very high current, very high current. Now, very high current means the current losses in the circuit will be I square R, R is the electronic resistance of the circuit, which means you have to reduce the electronic resistance of the circuit. That you can do. Suppose you are using it is flowing through copper, it has to be a very thick copper bus bar. So, that it will depend on the cross section, and therefore, you have to make very thick, provide for very thick wires to go through the current. So, as I said, there are these contradictions, that if you do this, you have one problem here. If you do that, you have another problem here, and the man in the industry, through trial and error, through their facts, information and knowledge, will acquire the wisdom to do what is right. And what is right? Industry, what is right means, first of all, what is workable, operations cannot stop. Whatever is done should be friendly to the technologies available. You can always come up with a lot of theories, but the technology says this is not possible. So, there should be technology to back up your wisdom. Your operational flexibility should be there. Floor space should be minimum. So, the industry has to play around with these contradictions, and this has been done. But even then, no two plants are alike, because there may be somebody who can handle one contradiction better than another industry which does another contradiction there. So, there are many aluminum plants where the arrangements are not all identical. There may be slight differences. When you come to production of actual metals, you will find nothing has been totally systematized. Basic principles are the same, because but then it all depends on the local conditions, the talent available, the technology available. Now, I will continue with this little more, that okay, what will the industry do? How will they handle this part, that you need multiple cells? How will you arrange those multiple cells? This I will consider in the next lecture. And apart from that, suppose you have a given cell which is suffering from a limiting current problem. Is there something we can do to increase that limiting current thing? Thank you very much.